In this video, we will discuss the instrumental analysis technique known as single crystal X-ray diffraction. This is one of the oldest forms of non-destructive X-ray crystallography. The purpose of single crystal X-ray diffraction is to determine the molecular structure of a single crystal. This can be divided into three subsets and are actually steps in the process of actually determining the structure of the crystal. The first step is to analyze dimensions of a crystalline lattice. This involves determining the unit cell dimensions, the positions of the atoms within the lattice that are directly related to the bond lengths and angles from atom to atom. Step 2 involves determining the structure of the crystalline lattice from the information that was gathered in Step 1. In the third step, comparison of spectra is used for crystal identification. Previously stored crystal spectra are used to indicate if the crystal is a new discovery or is already banked in the library. What is X-ray diffraction? We will first answer this question by looking at X-ray diffractometers. A simple block diagram will be used to describe the instrumentation of analysis. The first part of an X-ray diffractometer is the X-ray tube. This is where the X-rays are created in a cathode ray tube. By heating a filament, the cathode ray will dislodge an electron, which will attack a target such as molybdenum. The strong attack of electrons will produce X-rays that are then collimated and headed towards the crystal holder. The second part of a diffractometer is the crystal holder. This keeps the crystal in a fixed position and allows the X-rays to interact with the crystal. The X-rays are either reflected or refracted against the crystalline lattice. The angle of incidence of X-rays against the crystalline lattice defines the spectrum produced. The third and final part of an X-ray diffractometer is the X-ray detector. This is where the diffracted X-rays can be seen as spots against the detector. The spectrum is determined by these spots, which are known as reflections because they are the X-ray reflections off of the crystalline lattice. In this diffraction diagram, a three-dimensional view of the block diagram is illustrated. Beginning with the X-ray tube, denoted here microfocus X-ray tube, is where the target material is dislodged of electrons producing X-rays. The X-rays are then directed through a pinhole collimator or an X-ray monochromator. Passing through those, they reach the crystal holder, denoted here the sample holder. This is holding the crystal and allowing the X-rays to interact with the crystal. After the X-rays are diffracted through the crystal, they reach the X-ray detector, denoted here as CCD. Although this illustration depicts rings as being produced from the sample holder, there are actually spots in X-ray diffraction specifically. Let's take a look at the spectrum produced. For single crystal X-ray diffraction, the spectrum looks similar to this but is slightly altered. The x-axis is the same, denoting degrees, and the y-axis is denoting intensity. But in single crystal X-ray diffraction, the degrees are denoting the rotation of the crystal or the rotation of the detector. In order for X-rays to be properly diffracted, the angle of incidence of X-rays against the atoms in the crystal must satisfy Bragg's law. This is the formula for Bragg's law. The angle of incidence of X-ray, also known as Bragg's angle, is denoted here theta, and determines if Bragg's law can be satisfied. An independent research project, X-ray diffraction was used to analyze the growth patterns of nanoshapes such as nanospheres, nanocubes, and nanoflowers. In Figure A, we can see nanoflowers at 5 microns of a scale. In Figure B, we see the exact same nanoflowers but at a higher magnification of 500 nanometer scale. These nanoflowers were grown using solvothermal techniques, and they were analyzed by electron microscopy and X-ray diffraction. In Figure D, we see the X-ray diffraction spectrum with intensity on the y-axis and degrees of rotation of the crystal on the x-axis. X-ray diffraction was used in this experiment to show the molecular structure of the crystal before growth and the molecular structure after solvothermal technique being used for growth. Here are my references, and thank you for watching.